Today we are going to continue our discussion on heat and mass transfer problems with more than one independent variable. And we're going to go into a class of problem which is specifically related to the boundary layer theory. In full, it's looking at flow near solid surfaces by boundary layer theory. So let's first give you some kind of a schematic interpretation of what we're looking at here. So let's assume that we have some solid object that might have some random shape like this. So this would be our solid object. Okay, and now we have a flow that's flowing through, or not flowing through, but flowing by this solid object. Or this solid object is actually submerged in a flow of fluids. So let's try and draw that. Let's say we have flow coming in. And actually, you can imagine that the streamlines of the flow would somehow go through that solid object like this. So the closer that flow initially was to the solid object, the path of that fluid gets kind of compressed. Okay, so these blue lines here are called streamline of potential flow. So these are the streamline of potential flow. So potential flows are basically flows of a constant velocity, okay? And you can see that, because when you're at a, solid fluid interface at that boundary, you still have the no slip condition, okay? So what this means is that, you would have a velocity profile starting from no slip condition approaching the potential flow velocity as we are moving away from the solid surface. At some point, that velocity gradient disappears, then you reached into the potential flow regime. Okay? So we can kind of say that this up to this point here, we will be kind of approaching this distance here. We can kind of say that it is the approximate outer limit of boundary layer, where the velocity, which we'll cover in shortly, the velocity approaches the entrance velocity. Okay, so if we kind of define our coordinates better, so you can have a better idea what we're talking about, if we define that, the direction along the solid object as x, and the direction perpendicular to our solid object as y. Okay, so the outer limit of the boundary layer is where v sub x, so the flow in the x direction along the solid object, approaches those of, the bulk velocity ve of x. Okay, so let's kind of go through what's happening again. Here is that when you have a potential flow that's kind of flowing into the solid object, or if you can say that if the solid object is kind of, immersed in a flow, what happens is that, because you still need to fulfill the, what's called the, no slip condition, right? But that's going to happen within a very small distance. And within that small distance, the velocity is going to change from 0 at the boundary, no slip condition, gradually to the bulk flow velocity, v sub e. And in that region where that velocity is changing is called the velocity boundary layer here. Okay? So, and typically when we're dealing with boundary layer problems, we would define the coordinates as the direction parallel to the solid surface being x, and the direction perpendicular or normal to the solid surface being y. Okay, so let's bullet point that down of what we've just been describing. Okay, so maybe we'll write it starting from here. So basically, we will obtain and approximate solution for the velocity components in a very thin boundary layer. Which is near the wall or near the surface. This is also something I want to emphasize, that taking the viscosity into account, because in the potential flow regions, viscosity does not play any role there. So taking the viscosity into account. Why is that? Because as we remember when we say that in the potential flow, actually, it's all driven by pressure forces, and there will be no differences in the velocity between adjacent streamlines. So if you don't have velocity gradient, you do not have viscosity, or you do not have drag force. So viscosity doesn't come into play. Okay, so that's the first bullet point. And then the second bullet point is what? Is that to describe the thickness of the boundary layer, what we need to do is to figure out the thickness where the solution of the potential flow of the velocity matches the velocity that's described within the boundary layer. So that means at the outermost boundary of the boundary layer, the velocity will match with the potential flow. So that's kind of like your boundary condition. So the second point would be, match solution to the potential flow solution that describes the flow outside the boundary layer. Okay, that's our second point. And the third point is that the success of the boundary layer theory actually depends on the thinness of the boundary layer. So that means if the boundary layer thinness depends on a high Reynolds number. Okay? So here are the first 3 bullet points that I want to give you, is that what is a boundary layer, and how do we describe the boundary layer? It's basically a thin layer near the submerged object where you have the velocity gradient changing from the surface of that object and to a point where it doesn't change anymore, and it will be equal to the velocity of the potential flow outside the boundary layer. Okay, so let's now try to do some mathematical description of the boundary layer, and we're going to do some analysis, some assumptions to see how we can transform the equation of changes from, a ordinary 2D problem to a boundary layer problem. Okay, so now let's try to do that. So first we will consider a 2D flow, two-dimensional flow. And just for simplicity, let's say that it has constant density, constant viscosity, and it's going to flow around a submerged object. Okay, and from our previous description, we know that the velocity changes only in the boundary layer. Where curvature effects are not important. Okay, and remember that we've said earlier that we typically would like to define the direction parallel to the solid object being x and the direction normal to that surface being y. So that means that we can set up a Cartesian coordinate system. So we will set up Cartesian coordinate systems. And the key here is that x would be pointing downstream and y would be perpendicular to the surface. Okay, so just to, give you a better idea what's going on, let's say we have an object like that. Let's just look at the upper part of what's going on, and we have flow coming in. So the flows will kind of going through the streamlines, but slightly bended when it's flowing through the solid object. So now we would define this direction as x and this direction as y, and we will have some boundary layer where we have velocity gradients, but once we approach the most outer limit of the boundary layer, then it's becoming potential flow, so the velocity becomes constant with no gradients. Okay, so this part would be our boundary layer. Okay, so let's try to write down the equation of changes and see how we can, start from there and construct the equation of changes, customly for a boundary layer problem. So first, let's list down the equations. Obviously, we have the continuity equation. So continuity So for constant density fluids, we know partial, and a 2D flow. So, let's just start from the beginning. So we know that the gradient of rho v for a constant density problem, we'll take out the density as constant, equals to that times the gradient of velocity. And because it's a 2D problem, so we just need to consider the x and y components. So it's going to be rho partial vx partial x plus partial vy partial y equals to 0. So it's just saying that the equation of continuity just says that partial vx partial x plus partial vy partial y equals to 0. Now let's look at the equation of motion. So the equation of motion, we have what? Let's consider a steady state problem. So, let's just start from the beginning. We have the substantial derivative of velocity over time equals to -1 over rho, the gradient of the pressure forces, minus 1 over rho, the gradient of the shear stress tensor, and maybe some external forces like gravity. For a steady state problem, so let's say at steady state, then the left-hand side becomes what becomes, the time-dependent term vanishes, so it's just v gradient of v equals to 1 over rho negative gradient of p minus 1 over rho gradient of the stress tensor plus the external forces. Okay, and we can further deconvolute that into the x and y direction. So let's take a look at that. For the x direction, remember x direction would be along the streamline or pointing downstream. We have vx partial vx partial x plus vy partial vx partial y equals to -1 over rho partial p partial x plus mu over rho partial square vx partial y square plus partial square vy partial x square. Okay, and for boundary layer problems, you typically can neglect gravity terms. And then we have for also, let's try to list down the y direction. We have vx partial vy partial x plus vy partial vy partial y equals to 1 over rho partial p partial y plus mu over rho partial square vy partial x square plus partial square vx partial y squared. Okay, so here are our three, our equation of changes. One is right here, equation of motion. The conclusion is that partial vx partial x plus partial vy partial y equals to 0. We have the equation of motion deconvoluted under steady state to the x and y direction respectively, which is listed or highlighted here with the marker. So the next step is trying to see how we can kind of simplify the system. And we're going to do that with what's called the 3 yardstick quantities. Okay? So again, it's kind of like doing kind of like the idea of doing some kind of dimensional analysis, right? Remember, in the dimensional analysis, we would first want to list down the characteristic quantities, using that to do dimensional analysis. The first step here is kind of like that. We want to first identify some characteristic, or in here we call them yardstick quantities. Okay, so let's continue. So we want to do some simplification with 3 yardstick quantities. So the first quantity would be the approach velocity. Which is V infinite. The second quantity would be some linear dimension of the submerged body. Some linear dimension of the submerged body, which we would use, just say L naught. And the third one would be the average thickness of the boundary layer. Which we would use the Greek letter delta naught as a representation. Okay, and typically we will presume, very importantly, we will presume that the boundary layer thickness, or the average thickness of the boundary layer, are typically much smaller than the characteristic length or the linear dimension of that submerged body. Okay, so with this presumption, with this very important presumption, we can go ahead and perform what's called the order of magnitude analysis. Order of magnitude analysis. So we can use a, representing this by saying it's the analysis of some function x. So order of magnitude analysis of some function x to represent that. Okay, so here this O means order of magnitude. Okay, so with this presumption, let's take a look at, the terms in the equation of changes, and let's try to see what the orders look like. So first, let's take a look at the common term appearing in all equations. Let's take a look at partial Vx partial y. So we can kind of know that the order of this would be on the order of what? On the order of the approaching velocity v infinite, because Vx is pointing downstream. So it's very reasonable to use the approach velocity would be of the same order of Vx, right? And then for the y, because we're looking at boundary layer problems, so that order should be on the order of the boundary layer thickness. Okay, so here we have the order of magnitude analysis for partial Vx, partial y. Okay, and let's just, another reason for using V infinite is because at the boundary layer or outside the boundary layer, Vx actually equals to V infinite. Outside is one word. Outside the boundary layer. Okay, let's look at a second term here. Let's look at partial Vx partial x. So partial Vx partial x is on the order of V infinite and L naught. So immediately you can see, if you compare the two terms here, if you compare the order of, of partial Vx partial y is going to be much greater than the order of partial Vx partial x, because the characteristic or the boundary layer thickness is much larger than the characteristic velocity or the characteristic length of the submerged body. Now, further on, let's take a look at C, which is partial Vy partial y, which equals to the order of what? Equals the order of partial V infinite over L naught. Why is that? This is because, based on the equation of continuity, remember that partial Vx partial x plus partial Vy partial y equals to 0. So that means they must be of the same order of magnitude for the equation of continuity to hold. Okay, but in other words, the important analysis behind this is that we now know that Vy should be on the order of what? On the order of delta naught over L naught times V infinite. Right, because if Vy is divided by delta naught, then you have the order of V infinite over L naught. Okay, and that means Vy should be much smaller than Vx, which is on the order of V infinite. Okay, so here are something that we already can compare. We compare the orders of different quantities and different operators or the partial derivatives that will occur in your equation of changes. Okay, and with this having in mind, we will further analyze all the terms within our equation of changes. So we will analyze all terms. So we have Vx partial x. So this is describing the convection term on the left-hand side, which is on the order of V infinite over L naught. Similarly, we have Vy partial Vx partial y. It would be on the order of what? It would be on the order of Vy should be delta naught over L naught V infinite times V infinite over delta naught. So the delta vanishes, so it's still being on the order of V infinite squared over L naught. So they're actually the same, right? Now let's look at partial square Vx partial x squared. This equals to the order of V naught over L naught square, and partial square Vx partial y squared on the order of V infinite over delta naught square. Okay? Okay, and also if you look at the analysis here, we know from the equation of continuity, we know that the order of partial square Vy partial y squared should also be equal to the order of V infinite over L naught squared. Again, this is from equation of continuity. You can figure that out. So this gives us to another relation that the partial square Vx over partial x squared would be much smaller, will be on the similar order of partial square Vy partial y squared, and will be much smaller than partial square Vx partial y squared. Okay, so basically we have all the terms in our equation of change, especially in the equation of motion, figured out. Okay, so we have each term that relates to velocity and the characteristic length, meaning L naught or delta naught, figured out. Let's come back to the equation of motion and the x direction first and see what's going on. Okay. And because the equation of changes, or the equation of motion, is an equation, that means the left-hand side of the equation should be of the same order to the right-hand side. Okay, so, let's quickly write that down. So the important concept here is that for any equation, let's say for any equation, the left-hand side and the right-hand side should have the same order, right? So the left-hand side and right-hand side should be of the same order in the equation of motion. So if we look at the x direction first, we can now see that the left-hand side, which would be what? The left-hand side is Vx partial Vx partial x plus Vy partial Vx partial y. If I remember that correctly, let's double check that. Yes, so that's correct. Okay, so you can see that it would be on the order of what? It would be on the order, let's say left-hand side, on the order of V infinite square over L naught, right? And let's look at the right-hand side. The right-hand side, we now have the order of what? We have the pressure term, but let's look at the viscous term first. So the viscous term is what? The viscous term is right here. So we have mu over rho times partial square Vx partial y square plus partial square Vy partial x square. And it would be on the order of what? The kinematic viscosity, being the viscosity divided by density, and partial V square Vx partial y square would be what? Would be V naught over delta naught square. Okay? And since the left-hand side must be of the same order of the right-hand side, that means what? That means the order of magnitude of V infinite squared over L naught would be equal to the order of the kinematic viscosity times V infinite over delta naught squared. Okay, so that also shows what? That also shows that the order of delta naught over L naught would be of the order of the square root of the kinematic viscosity over V infinite times L naught. And this actually equals to the order of 1 over the square root of the Reynolds number. Okay, this is a very important result that shows us that, the ratio between the boundary layer thickness and the linear dimension of the submerged body will be very small at high Reynolds number. And obviously we cannot forget that on the right hand side we also have the term that's going to be what? It's 1 over rho and partial p partial x. And that also should be on the same order of, V infinite squared over L naught. Now let's look at the y direction. So y direction. Again, we will do the same analysis. So let's look at the left hand side. We have what? We have Vx partial Vy partial x plus Vy partial Vy partial y, which is on the order of what? On the order of V infinite squared times delta naught over L naught. Okay, and so you can look at the left hand side now. It's already much greater than the right hand side, right? So let's just do the whole analysis. So the right hand side, we now have what we have. Looking at the viscous term again, the viscous term is basically the same as the previous one. So mu over rho partial square Vy partial x square plus partial square Vx partial y square. And that's on the order of the kinematic viscosity. And again, we have similar terms here. So we have V infinite over delta square. And we know from the previous analysis that it's on the order of V squared over L naught. So it would be on the order of V squared over L naught. I noticed that I made a mistake somewhere, so let me try to make this correction real quick. So let's come back to the equation of motion. I think I've written this incorrectly. So these are all Vx and these are all Vy in the equation of motion. Okay, so coming back here, this is also Vx. And these are all Vy. So the only thing that and okay, so let's go over the y direction again, just to make sure we are, passing on the correct information clearly. So again, let's start from the left-hand side of the equation of motion on the y direction, or in the y direction, which is written down here. So if we analyze the problem, we probably should look at both terms. So let's see. This would be on the order of what? This would be on the order of v infinite, and previously we already write down that vy would be on the order of delta naught over L naught v infinite, and times 1 over L naught. So that's the order of what? On the order of v infinite delta naught square over L naught square. If we look at the y term here, again we have delta naught over L naught v infinite square divided by delta naught. This is also equal to the order of v infinite over L naught square times delta naught. So this equals to the order of v infinite squared times delta naught over L naught square. That's for the left-hand side. Now let's look at the right-hand side. So on the right-hand side, we have what? We have, looking at the viscous portion, we have the order of the kinematic viscosity times partial square Vy partial x square plus partial square Vy partial y square. Now, we know that the L naught, this is L naught in the denominator, right? And this would be delta naught in the denominator. So the first term can be safely neglected because it has a much larger denominator. So we'll neglect that. And from the equation of continuity, we know that the order of partial square Vy partial y squared would be of the same order of partial square Vx over partial x squared. And we know that this would be much smaller than the order of partial square Vx partial y squared. So from our previous analysis, we know that the order of the kinematic viscosity times what? Times partial Vx squared partial y squared. This one would be equal to the order. This would equal to the order of, up here, equal to v infinite square over L naught. And it will be much greater than the order of kinematic viscosity and partial Vx partial x squared, which equals to the order of kinematic viscosity times partial square Vy over partial y squared. Okay. So, with this in mind, you can see that the order of magnitude analysis of the y direction already has a much smaller value because this is much smaller than the order of v infinite square over L naught. It's basically this multiplied by delta naught over L naught, right? Okay, so that tells us something. That tells us that the order of magnitude of the equation of motion in the y direction is significantly much less impactful than the x direction. Okay. So finally, the analysis shows that the y component of the equation of motion is much less impactful and is not needed. Okay, and this also gives us another conclusion or another result that says the modified pressure can be treated as function of x only. Maybe we use a different color for this. Okay, so the conclusion is that we can kind of say that because after the order of mathematical analysis, the order for the y direction equation of motion, the order of the equation of motion in the y direction is much less or much smaller than the equation of motion in the x direction. So we'll neglect the y direction. It can be safely neglected. And so we're left with what's called the Prandtl boundary layer equation. So we are here left with the Prandtl boundary layer equation. So we have the continuity being kept the same, which still holds partial Vx partial x plus partial Vy partial y equals to 0. And we have the equation of motion being Vx partial x plus Vy partial Vx partial y equals to -1 over density partial P partial x plus the kinematic viscosity times the Laplacian of partial Vx partial y squared. Okay, and the important thing here, a note, is that the pressure here is presumed known from the solution of the corresponding potential flow problem, or from experimental measurements. Okay, and let's now also list down the associated boundary conditions. So boundary conditions. The first one would be still the no slip condition always holds. So v of x equals to 0 at the surface, so at y equals to 0. 2, we have no mass transfer from the wall, the solid object. So we have Vy equals to 0 at y equals to 0. 3, we have the velocity will be approaching the incoming velocity or inside the potential flow. So Vx of x and y will approach Ve of x at the boundary layer edge. And 4, we have Ve of x is a function of pressure by the potential flow equation. Okay, so the last term is important here. So the last term here tells us that the term -1 over rho partial p partial x can actually be replaced, by VE times partial VE partial x. So this is from the equation of motion from the potential flow for steady flow. Okay, that's because for a steady flow in the one dimension, VE dVE dx is only driven by the pressure gradient, so 1 over rho dP dx outside the boundary layer. Okay, so with that said, the equation of motion from the Prandtl's boundary layer equation can be further modified or simplified. So equation of motion in the boundary layer becomes Vx partial x plus Vy partial Vx partial y equals to V sub e dVE dx plus the kinematic viscosity times partial square Vx partial y square. Okay, and the other thing that's very important is that from the equation of continuity, we know that Vy would equal to the summation of, equal to the integration from 0 to y times partial Vx partial x dy. Okay, so we will substitute this into the left-hand side. So now we have Vx partial x minus summation from 0 to y partial Vx partial x dy times partial Vx partial y equals to V sub E dV sub E dx plus the kinematic viscosity times the Laplacian of Vx, or the double derivative of Vx over y. Okay, and what's next? What's next is we will use this to obtain the von Karman momentum balance. Okay, so, if we multiply by density and integrate from y equals to 0 to y equals to infinite, we would get the very famous von Karman momentum balance. Okay, and it is actually the basis of many approximate boundary layer solutions, which writes down as the following. We have going to be mu, because we divide everything by density, now we're left with the viscosity partial Vx partial y, and we already integrate from y to 0 to infinite, at y equals to 0 equals to d dx times the integration from 0 to infinite rho Vx times Ve minus Vx dy plus dVe dx infinite to 0 to infinite integration rho V sub e minus V sub x dy. Okay, and physically, the left-hand side would be what? Because you're looking at y equals to 0, so this is the shear stress exerted by the fluid on the wall. Okay, so let's take a break here and we will come back with some example problems.